So welcome back, everybody. And the topic for this week is to get started with neural networks, which is our first example of deep learning methods. And that's going to, as I said yesterday, this is going to keep us busy for at least the next month. Now, the topic today is actually to go through the exciting, gritty, nitty details of a neural network and how to set it up and how to define what's called the backpropagation algorithm, which is the central algorithm which allows us to update the parameters of the network. So yesterday, we looked at cases where we could classify correctly a so-called OR gate, where you have bit 0 and 1, which are given as input, and then we can get bit 0 and 1 as an output. We had an XOR gate, and then we had an AND gate. Now, in the case of an XOR gate, what we saw is that if we wanted to use a linear model to find a line which separates the different outputs, we couldn't do so. So the XOR model was a typical example of what we would call a nonlinear, or something which needs a nonlinear model. Now, what we're going to do today is to continue a little bit with the basic definitions. We are going to look at some of the important ingredients in a neural network. We're going to discuss the architecture, which defines our model. And then we are going to set up the mathematics, which is needed for the backpropagation algorithm. And with that, next week, we are then ready to make our first implementation of a neural network. And next week, if we get time to it, we will also look at how to use neural networks to solve differential equations, which is a pretty hot topic. But the basic thing next week is actually to implement the different algorithms which are needed and which we will describe today. So I'm going to jump a little bit back and forth between the whiteboard and slides, but I will mainly stay with the whiteboard because we have some mathematics which we have to go through. Okay, so that's basically the plan for the day. I mean, feel free to ask questions if you have some questions, and then I'm going to go back to the whiteboard. So what we did on Thursday was to set up some of the basics of a neural network. So we defined what we call the input layer. So that's our X values, and which we have typically in project number 1 defined in terms of a so-called design matrix. Now, normally for neural networks, the design matrix now is just going to be the raw data we feed in. You could, if you want to, if you think of project number 1, you could actually feed in a design matrix. So that's fully possible. But then you're forcing the network to find the parameters of a model which you have made, which could be a polynomial. Whereas what we want the network to find is, in a kind of unhindered way, to find the optimal parameters which describe an ideal function which we think describes the data. So there are some differences in philosophy. So typically the input of neural network is your raw X data. This raw X data could be a classification problem where you have different features, and every feature with every observation would then be one input to the network. And then, as we said yesterday, we could have a so-called simple perceptron model where we just feed something in, we modulate it, and then we send an output. Now, this is something which we, in discussions yesterday, we showed that this is okay if we have a typical linear problem. That means that we have a problem which can be approximated, for instance, with a first-order polynomial. But if we have nonlinear complexities, then that kind of approach fails. Now, one of the things which we mentioned yesterday was the universal approximation theorem, which plays a central role in neural networks. And that states that you can approximate a continuous function to a specific error if you have at least one hidden layer. Now, the way we wrote the network yesterday was in a very compact, with a compact graphical, in a compact graphical way. So we had the inputs, which can be given by a vector, or they could be given by a design matrix if we have many features. Then every feature would be a column. Next week, you're going to see an example of how we would set up the inputs for an image. So an image in 2 dimensions has a number of pixels in the X and the Y direction. And the pixels, each pixel would then represent one value of X. So if you have an image which has 8 times 8 pixels, 64 pixels in total, you would have 64 input values for that image. If you have more fine pictures with 200 times 200, then clearly you would have 40,000 inputs to your network, and so on. So just so that you get a kind of feeling of what your inputs looks like. If you think of a one-dimensional function, if you have 100 input values, then you have 100 x1s, x2s to x100. With x and y, with the Franke function, then you simply need to add the y values as well. And these will be your inputs. And graphically, this is often written in a compact form like this, and we could have many hidden layers. So let me just also put up here neural networks. And then these hidden layers, they produce an output. And what we call these different layers is, this is the input layer, pretty obvious. These are the hidden layers. And the way it's written now is just in terms of one hidden layer. But you could think that this H represents a series of hidden layers. I'm just going to put S here. And then we produce an output, Y tilde. And this is normally called the output layer. And then we have the targets. So we have T, this is what we want to reproduce. So previously we just called these the outputs. So I'm going to interchangeably use outputs and targets, but I'm going to use the symbol T to indicate that this is the target we want to reproduce. And in these kind of graphical ways of representing it, you would have an arrow into the output from the network. So this is pretty common in the field. Now, what we are going to look at now is something which in the literature you will often find with different types of names. So sometimes it's called a multi-perceptron network. And this is normally a multi-perceptron layer network. This is often something you will see in a shorthand MLP. You will also see another way of writing it. So this is a feed-forward neural network. Forward. And NN is something which I will use for neural network as a shorthand. And you will often see the shorthand FFN N here for a feed-forward neural network. So when people talk about a multi-layer perceptron model or a feed-forward neural network, this is normally the same. In scikit-learn, you will see a functionality which is called MLP regressor or MLP classifier. So you can use them for classification problems or for regression problems where you want to fit a function. Now, if we now look at the parameters which we need to fit, so our parameters are the weights and the biases in a network. And these are normally condensed into this variable theta, and these contain the weights and the biases. And when I write it in this compact way, the weights would typically be the weights for all the hidden layers. And the biases would be the biases for all the hidden layers. So let's look at the general architecture which you are going to encounter and which you actually are going to program in project number 2 here. By the way, project number 2, if you wish to peep into it, if you're not too stressed with project 1, that should be available online. So you can take a look at it. And project number 2, the way we build up these projects is that they are kind of continuations of the previous one. So you can reuse things you have developed in project number 1. And the first step is actually you using a polynomial, trying to fit that, but instead of inverting the matrix, you're going to calculate the gradients with a gradient descent and a stochastic gradient descent method. And the reason for that is that you're going to apply this in the calculation or your setup of a neural network. So the neural network is going to be the main issue or the main topic for project number 2, where you actually develop your own neural network. But we're going to step us through it by first writing a gradient descent algorithm, which we then use in the neural network. Because for the neural networks, we don't have nice analytical expressions for the gradients normally. Okay, so if we now make a drawing of what we have, you would typically see the input layer being written in terms of a box like this, and then you would have a series of input nodes, x1, x2, down to some xn. So we would have an xn here, we have an x1, x2, etc. Then we can have a series of hidden layers. So we would have a hidden layer here, and we call this L1. So this is the first hidden layer. We have a new hidden layer and a series of hidden layers. Here we have layer L. So this is just an L. And this continues till the output layer. And I'm going to put a label L here, uppercase L. So that's my output layer. So this is the output. The final layer is normally labeled as the output layer. So this is the output layer. And that produces a value y tilde. And this is now being confronted with the data which we have, the targets. And the output layer can have many different nodes itself. If we are just producing one output, there will just be one output in the output layer. If we are doing a classification problem with 10 possible outputs, like the handwritten numbers from 0 to 9, then we would have 10 outputs. Now, the hidden layers can have as many nodes as you want, but clearly the more nodes you plug in, the bigger the complexity of the model, and the more tricky the optimization problem itself. So what you end up with then is a series of layers here, and you could now think of these different nodes, which we are going to label with an L to indicate a specific hidden layer, and then we would have N1 hidden nodes here, we can have NL hidden nodes, and then we have the output layer. And typically what we would have now is that if we look at the specific point here, in this layer, so we set up this as a node I. This would typically feed in to the next layer to all the nodes. So that means that all the nodes are connected. Now this connectivity means that you can rewrite everything as simple matrix operations. However, this becomes pretty heavy if you have huge numbers of data. So if you're doing image recognition and you want to have high resolution images with, let's say, hundreds of pixels, and you have 1 million of images, you can quickly see how big the training data becomes. And if your design matrix is going to represent all these images, then it's going to be a monster. And you will have tons of such matrix multiplication, which are really dense. So a typical neural network is something you would never apply to these huge problems. And that's where convolutional neural networks kick in, which is a way to actually filter out some important features. So if you want to classify houses, I mean, there's no point in keeping all the pixels because many of the pixels just represent the wall and the wall has just a color. So you would normally have pixels which represents corners, the roofs, windows, and so on. And then you can reduce, you can filter away a lot of information. But here, with a standard neural network, we are going to look at us using all the data we have. And all the nodes are going to be connected. Okay, so if you look at that specific node here, I, that feeds in to a node here, which we can call for J. Now this node J here receives information from all the other ones. So all these feed into that one. And the kind of input to that specific node is something which we are going to label as a Z. So input to node J in layer L. So this is a hidden layer. So that's the hidden. And we call this layer L from layer L minus 1. We are going to label this as a Z, and it has a subscript J, and it has a superscript L. And this is going to contain a sum over all the contributions from the previous layer. And now I have n of L minus 1. So that's the number of nodes in the previous layer. And this contains now the weights of Wij of L multiplied with a quantity which I'm going to define here, L minus 1, plus this bias, J of L. So these are the weights which we need to determine. This is what we call the bias, which is often set in here in order to avoid that in case the weights are 0, that actually you're moving the data through the network doesn't stop. So the bias is a way to hinder that, for instance, the training of the network stops up in the middle of the layers. Now, this C is now the input to node J in layer L. This A here is the output. So AIL, that's the output from node I in layer L minus 1. So what we're doing now is that we are modulating the output from a specific node in the previous layer with a weight. And that feeds into that specific node in the next layer. This is one of the basic quantities which we need to set up. We need to initialize the weights and the biases. That's one of the typical things we need. So the weights connect a layer L minus 1 with the next layer. And this A of I, L minus 1, that's the output from a node in a layer L minus 1. Now, what we also need to define now is the output part and the cost function. So let's go back and try to set up the definitions of quantities which we need. So we need to define a cost or loss function. And let us assume now that we look at a regression problem. In our case then, C of theta is now going to be given by 1/2. I'm skipping the n term, and it has a sum over all the data which we have up to n. And then I have my output from the final layer. So this is my output, what we previously called y of I tilde. So I'm just going to introduce a slightly different notation from what we had before. So this A is now what comes out from the output layer, from a specific node. So if you have just one output, suppose you put in x1 and y1, that gives you an output in the Franke function. So that would just be one value, just to give you an example. And this quantity here is normally generated by some activation function. When you're doing a regression problem, you don't plug in an activation function. You just hand to the cost function the output value which you get. Whereas when you do a classification problem, you're going to deal with a threshold and you're going to say, okay, if it's less than 0.5, I give it a value 0. And if it's larger, I give it a value 1. like we discussed yesterday with these different gates. And then we have the target, T of I, and this is squared. So that's the typical example of the cost function which we have seen before. When we come to classification problems, we are going to look at this cross entropy, which we introduced with logistic regression, and we can modify that one to classification problems with more than just two classes, more than a binary problem. Then, if we now continue a little bit with the definitions, we are going to define this output of AJL, a given a node in a specific layer. We are going to define that by a function which we yesterday called the activation function. So this function which you see here is called the activation function. And this becomes something which we are going to deal with as parameters in terms of functions. And this is something which is not set in gold or set in stone. What is the relevant activation function? And this becomes a kind of function parameter which you are going to play around with. And for some cases, you may find that the sigmoid function which we have discussed gives the best result. In other cases, this function which we mentioned yesterday, the so-called rectified linear unit, gives better results. And this becomes one of the inputs to your parameter space in your optimization of a specific data set. So many people get a little bit disappointed when they see the plethora of complexity in terms of parameters, functions, things you have to tweak and tune in order to get the best possible mean squared error. And we are coming back to these things gradually. So the activation function plays an important role. If you're doing Bayesian statistics, you can actually replace these activation functions with a probability distribution. So Bayesian statistics and Bayesian machine learning, or Bayesian neural networks, they try to find the best probability distribution for giving a specific output. That becomes, from a computational point of view, much more time intensive and CPU intensive. So many people just end up with playing around with standard neural networks and just dealing with different activation functions. Okay, so we're also going to look at the more compact notation. So we wrote this set J of L. We can write it in a vector notation. So previously we just put it up here in terms of the subscript J. But now we can think of this as a vector because you have a given number of nodes in every hidden layer. So that means that if you have n nodes, then you have n elements in a vector. So you will often see these things in a more compact vector matrix notation. And one way of writing this is in terms of the matrix, which contains the weights for layer L transpose multiplied with the vector of the outputs from layer L minus 1 plus the vector B, the biases for layer L. So I'm just bringing up some notations now. A popular activation function is the sigmoid, as I mentioned, and we're coming back to that one. Activation function is the sigmoid, and the sigmoid is defined as, so we would have a sigma z l j l here, which is then simply 1 over 1 plus e of minus cjl, and this defines the output from node j in layer L. So what the things which we are going to need now, actually the basic ingredients in a feed-forward neural network are the followings. The basic ingredients. in a feed-forward NNN or a multi-layer perceptron model is, one, the feed-forward stage. So that means the following. What we do then in the feed-forward stage, if we go back to the image which we put up of a neural network, it means that what we would do then is simply to run through the input layer. We modulate, we give some initial values to the weights and the biases. So this is something which we have to initialize when we're setting up the network. You have an initial value for the weights and the biases, and then you feed the information through all the layers till you produce an output. Now, this output is then compared with the target. And then when you have the targets and the outputs, you can compute the mean squared error. Then you take the derivative of the mean squared error, and then you propagate backward till the first layer, and then change the gradient gradually, or layer by layer. And then you have new gradients, you have new weights and biases, and then you do a new feed-forward stage. And then you go back and forth till your mean squared error, for instance, doesn't change by a prefixed amount which you have settled upon. So there are basic two stages which we're going to set up the mathematics which are needed in order to set up the neural network. So the first stage is we feed information forward, produce an output. Then we have what's called the back forward or the back propagation algorithm or the back propagation stage. And this is where we train the weights to train the parameters theta. Now this has two basic elements here. So one is what's called the back-forward propagation algorithm. And the back-forward propagation algorithm is actually a way via the chain rule to calculate expressions for the gradients. So that gives you the expression for gradients. Of the cost function of C as function of layer L of the various layers. And as you will see, this entails a repeated implementation of the chain rule. So actually what we are going to see now is just a plain implementation of the chain rule. Nothing more than that. So it doesn't sound very exciting, but it's actually an extremely useful algorithm. And it's at the heart of all the machine learning methods which deal with neural networks, whether these are convolutional neural networks, whether they are recurrent neural networks, whether they are adversarial neural networks, and so on and so on. So inside somewhere, you're doing the back propagation to train the parameters. Now, this gives you expression for the gradients. And when you have the gradients, you do actually the optimization with the gradients. And that means that you're implementing some gradient descent or stochastic gradient descent. And here we have the second stage, which is the gradient optimization. So we can do a stochastic gradient descent, SGD. We can have momentum, all the elements which we discussed last week and partly yesterday, momentum, adaptive, etc., etc. So this is a way, the back propagation algorithm is a way to find the expression for the gradients so that you can propagate backward till the first layer. Then you have updated all the parameters, all the weights. Then you do a new feed-forward pass. You produce a new output. And then you propagate back again, and you update the weights and the biases. And you continue with this till the difference between your targets and the output is smaller than a number you have decided upon. Okay, does that sound reasonable? So we need a recipe to find a way to update the weights, and the backpropagation is the standard recipe for doing that. So we would then repeat with feed forward, and backpropagation, and backpropagation in order to update the weights and the outputs. To update the weights biases, theta, so I'm just writing this in terms of the parameter theta, till our cost function, or our cost function, in our case for the regression here, reaches a converged value. So that's the basic of the kind of overarching picture which we can have of a neural network here. Now, what we are going to wait a little bit with, so what I want to do now is actually to set up the algorithm first. And then when we've set up the algorithm, we are going a little bit back again, and we are going to look at problems which we will encounter. So typical problems which we will encounter in the training is that the gradients can vanish. Because if the gradients vanishes inside a given layer, then the training of the weights stops up. And the process won't continue between this feed forward and back propagation. So the vanishing gradient is actually a big problem in neural networks, and we are going to look at some simpler examples here. But first, we are going to set up the equations which need to be coded. When we have these equations, we are going back a little bit, and we are going to see what kind of problems we are going to encounter, how we can solve these problems, and then we're also going back to the universal approximation theorem and what it actually means for us. We are not going to prove it, but we are going to use it. So the universal approximation theorem, and I'm just going to repeat it now, is an extremely powerful theorem because it says that we can approximate a continuous function f of x in terms of at least one hidden layer in a neural network. And we can actually approach this with a complex nonlinear function, which is represented by the network. And we will see next week, when we are going to look at differential equations, that we can actually solve differential equations using a neural network as an ansatz for the solution. And if you think of differential equations, we have a left-hand side, dx dt is equal to y. So you would start with a guess for y, and then you simply calculate the difference between the left-hand side and the right-hand side, till that difference is as close to zero as it can be. That's the recipe for using neural networks in the solution of differential equations. And that's a very active research field. Okay, we're coming back to that next week. But now we are going to take a look at the basic algorithm which we are interested in. So let's derive the backpropagation algorithm, and next week we are going to implement it. So what we are going to have, just to remind you, we have this definition of the input to a specific node in a given hidden layer L. So we have the sum over all the contributions from the previous layer. So we have these weights. So we would have a weight here, which is ij of L. And then we have an ai of L minus 1. And then we have this bias bj of L. And then we have defined this ai as the output from layer L minus 1 and node I. This is now the output of the activation function, which takes as input L minus 1 for node I. Now, if you look at these equations here, what we are going to do now is simply to set up a repeated usage of the chain rule, nothing more than that. And that means that we need partial derivatives. So let's look at the mathematical ingredients which we need. So one quantity which we can immediately read off from the equation for Z here, is CJL with respect to the weights Wij, and we can read that off immediately from the equation here, because now we have fixed a specific weight Wij, that is fixed, and if we just read it off, we see that this has to be equal to Ai of L minus 1. So I guess that's pretty straightforward. Then we need another derivative, so the quantities I'm putting up now are kind of intermediate steps which we are going to need in the calculations. So we have a dz of j of L of dAi of L minus 1. So we go back to the equation again, and then we fix Ai, so we're looking at the specific value, I, and that means that this simply has to be equal to Wi of j for layer L. That sound okay? No big surprise? So the next thing we need now, we need an intermediate result as well. So we need the derivative of the output from node J in layer L with respect to this quantity Z, the input. Now, if we now assume that this Aj of L, this is given by this function, this so-called activation function, which is a parameter in our neural network. So we need to decide upon a function here in order to find the expression for the derivative. And in this particular case, we could now assume that this is the famous sigmoid function. So if this is a sigmoid, we could simply write this as a 1 plus z minus z of jl. And you see quickly then that if I take the derivative of this quantity, is d alpha j, not alpha, but a, sorry for that, a jl of dz jl. If I take the derivative of the sigmoid function, this is actually going to be equal to sigma of L of zjl of 1 minus a sigma of zgl, like this. So it's not so difficult to see that. Now there's an intermediate step here which becomes important when you're writing a program. One of the few things you need to change when you write a program is a derivative of the activation function. So if you change activation function, what could be convenient is actually to introduce a class of activation functions, and where you just have plugged in the functions and their derivatives. Because this quantity which we have listed now, this is the partial derivative of the output from a given layer, is something which will be defined by your activation function. So keep this in mind when you write a code. What you see here is the explicit result with the sigmoid function. And this thing is something which will change with respect to changes, with respect to the chosen activation function. And it can be convenient now when we, after the break, we are going to go through the list of different types of activation functions. And then it's convenient actually to make a class or whatever, where you list different functions you want to use and their derivatives. Because this is a calculation which you will need many, many times. And then it's just easy to have this tabulated in some way or the other one. Okay, so what we have then is this specific function here, and we can actually rewrite that if you now think of the activation function being equal to, we have simply stated this. So in this specific case, what we would have is that this becomes actually a jl multiplied with 1 minus a jl. So in the example, which I'm going to run through now, I'm going to use the sigmoid function. But then when we set up the general equations, we are going to go back to the definitions of the derivatives. So, but for the sake of the kind of derivations here, I'm going to stay with the sigmoid function. Now, what we need next now, let us assume that we have done the first feed-forward pass, and we have reached the output layer. So let's look at the result which we would get when we have produced our first output. So this is the output layer. Now, when we have reached the output layer, we have obviously the C of theta, which we have defined for this regression problem in terms of a sum over I, and then we have the AI of L minus the targets, and this is squared. Now, what we are going to need now are the following quantities. We are going to need, in order to calculate the gradients, because remember now that what we are going to do is the same thing which we did with linear regression and logistic regression. We need to calculate the derivative with respect to the parameters. And in our case, the parameters are the weights and the biases. So what we need then is a derivative with respect to the weights, Wjk of L. And if we take the derivative of that quantity, what you will see now is that this is going to be given by A of L minus T of I. And this is multiplied with dAj of L, and then dWjk of L. Now, in order to calculate that one, we can use the chain rule. So this is where the repeated application of the chain rule kicks in. So let's now look at how we can obtain that. So we can now, if we now look at dJ of L, of dWjk of L, we can rewrite that one as a d of aj of L, and then we have an intermediate step which we know the results of. We actually did that one just some few lines ago, and this is given by Wjk of L. And you see now that we have, if we go up a little bit, we have already calculated this quantity here. We have that one. So that's what we would need to plug in here. So that is known. Now, this quantity here is also a quantity which we calculated when we set up the first equation here. So let us quickly remind ourselves about what that one looks like when we just plug it in. So this will now be given by aj of L of 1 minus aj of L. This is for the sigmoid function. And then if I go and pick up this term, this is given by ak of L minus 1. Now you can, if you want to be a little bit more formal or more general, you would write this as a derivative of the activation function Cjl of dCj of L. So if you change from the sigmoid function, the only thing you need to plug in is the derivative of the activation function. So let's do one more piece before we take a small break. So if I now go back and if I plug everything in here, then I can find the derivative with respect to the coefficients jk of L. So this is going to be equal to aj, the output, minus the targets which we want to reproduce. And this is multiplied with aj of L, 1 minus aj of L, and multiplied with this parameter ak of L minus 1. And we can rewrite this one in terms of aj of L minus tj. And then we have the term here, this term, which is nothing but the derivative of the activation function as a function of Cj of L, and multiplied with this parameter ak of L minus 1. And then it's common to define this term, J delta, and then after that one we're going to take a break. So this is going to be given in terms of sigma derivative, Cj of L, multiplied with Aj of L minus Tj, which actually is nothing but sigma derivative, the activation function derivative with respect to the specific node, multiplied with the derivative of the cost function with respect to the output from the last layer. So this is just another way you will see this parameter delta being written. And we are going to use this parameter in the equations which follow after the break. So this was the first step. So this is one of the first quantity which we need. We have now calculated the derivative of the cost function with respect to the unknown weights at the final layer. Then we need to propagate this backward so that we can update the weights. And that's the back propagation algorithm, which we will derive after the break, the final steps. So again, as I said, this is just a repeated application of the chain rule in an ingenious way, which allows us to update the unknown parameters. So we're going to take a small break. I'm going to put the recording on pause for those of you which are online. So we need to go through these nitty-gritty details about the backpropagation algorithm, which is simply just a repeated usage of the chain rule. So the first step which we have is this equation which you see here for this small change. And with that one, we can then find an expression for the derivative of the cost function in terms of this parameter delta L. Now, this parameter delta L is often written in a vector notation. Now, just keep in mind that when we rewrite it in vector notation, so when we take that, then what we have is a delta of L, and then we skip the subscript J, and we have the derivative. So we have a derivative with respect to L. But now, since this is a multiplication between two scalars here, we write this as a Hadamod multiplication, which means that we multiply component by component. And just to remind you of what this Hadamod multiplication is, we defined that last week. So this would just be the product of the respective elements. So this would simply be x1 times y1 and x2 times y2. So these are things written in a more compact notation where we skip the subscript. But when you're writing a program, you may actually end up having to look at the different subscripts. Or you could write everything in terms of compact matrix vectors multiplications. Now, the thing which we have now, and we can frame in this equation, when we bring everything together, is that we have the first equation which we need to set up, and that's the derivative with respect to the weights in the output layer. And this is given by delta J of L of A K of L minus 1. So let's just frame that in. So this is the first equation which we need. Now, another thing, and I leave that as a small exercise to you guys to show that. So let me give you the intermediate steps. So this delta J of L is actually given by dc of dc here, J of L. And this is something which we can rewrite in terms of the chain rule, in terms of Aj of L, multiplied with the partial derivative of Aj of L, and derivative with respect to Cj of L. Now, what we can also do is to set up this delta JL in terms of the derivative of the cost function with respect to the bias in the output layer. And this is going to be a dB of J of L of dC of J of L. And since C does not depend on, or B doesn't depend on Z, then this is simply given by dC of dB J of L. So we have an expression also in terms of the gradients with respect to the biases. So if we collect all results for L equal to uppercase L, what we have then are three equations. So we have the derivative with respect to the weights of J, K of L, and this is given by this parameter delta JL of the output from layer L-1 of node K. We have this quantity delta J of L, which is simply given by the derivative of the cost function, no, the activation function at this specific layer multiplied with the derivative of the cost function at the output layer. And then finally we have this quantity of dC dBJ of L, which is just equal to this quantity JL. So these equations which you see here, these are three of the important equations which we need in order to perform the back propagation. Now we have the equations which are needed for the output layer. Now we need to propagate backward. So we need the derivatives at every single hidden layer. And that's what we're going to set up now. So in order to get the equations for L different from the output layer, so now we're going to change this. So L different from L. We need a further equation here. So one of the things which we're going to do now is simply to remind ourselves that this delta JL is simply going to be given now if we use a definition of Cj of little l. And we can write this in terms of the previous layer. So we can have a cost function derivative at zk of L plus 1. So I'm just using the chain rule here. And this was a trick which was done in order to derive the back propagation algorithm. So I have a C of K of L plus 1 with derivative with respect to C of JL. So it just we just sum over all the nodes in layer L plus 1, and we want to propagate back to the layer L. And then we just sum over all the contributions, and we use the chain rule in order to define this contribution here by summing over all the nodes in the layer L plus 1. Now, we know this quantity here. This is a quantity which we have already defined. So this is this delta K of L plus 1. So what I need then, when we write it out, we need to calculate the second term. So this one is something we can rewrite in terms of L plus 1. And then I have a ZK of L plus 1 of dCj of L. And then we need now to remind ourselves that Cj of L plus 1 is actually given by a sum over 1 equal to NL, the number of nodes in that specific previous layer. So we would have a Wij of L plus 1, and this is multiplied with AIL plus Bj of L plus 1. So this is a definition which we used. And now you see that if I take the derivative of that quantity with respect to ZJL, so that means I'm going to take the derivative of the quantity here with respect to this quantity. What I need to remind myself then is that this is a function of Cj of L. Okay, so that means that the only quantity which now depends on Cj of L is this quantity you see here. So if we plug it in, this quantity Z derivative of zk of L plus 1 of dzj of L. This is nothing but the weights kj of L plus 1 multiplied with the derivative of the activation function. That's pretty easy to set up. So what we have then is the final stage. So we have a parameter delta j of L, which now depends on the results from the previous or the layer ahead of it. So that's going to be given by delta k of L plus 1, which we can calculate. We have the weights from the previous layer, L plus 1, which we can also calculate, or which we have calculated. And then we have the derivative of the activation function, which we can calculate. So these quantities are now going to go into the definition of the gradients. So this is what you see here, this final equation, together with the three previous ones. So let's frame this one in as well. This equation here, together with those which we had for the output layer. So if you look at these three equations here, this one, that one, and this one, together with the final equation which you have here, these are the key equations given by the back propagation algorithm. So when we have set up these equations, we are now ready to start looking at the algorithm for constructing the weights and finding the weights of a neural network. Any questions so far? This is just a repeated application of the chain rule. So when we have that and the derivatives, we can now set up the algorithm, which will then also use gradient descent or stochastic gradient descent. And that's where all the kind of discussions which we've been having come in concerning the gradient descent discussions which we have. So what we need now when we are going to set up the algorithm are the following ingredients. Now, one, you need to define a model, which in our case translates into the architecture. So that means the following. It means we need to specify the number of hidden layers, and we need to define the number of nodes in the layers, or number of neurons, as we've also been calling them. So these quantities, they define the architecture. So when you look at the polynomial complexity in linear regression, that is your model. In our case, the model is the complexity or the depth and the width. So you can think of the depth as a number of hidden layers and the width as a number of neurons which you have, or nodes which you have. So the depth and the width of the network define our model. And we can simply call the model the architecture of the network. But then we have lots of things which come in addition, so which we need to set up. So we need to initialize. So this is before we start performing the iterations. Initialize W and B. And we are coming back to how we initialize these next week, because this is going to be related a little bit to this topic of vanishing gradients. So, but we can initialize them. And the standard way to initialize them is to use a random distribution which follows the normal distribution. And we tend typically to use small values around 0, so from minus 0.5 to plus 0.5. This is just to have something the network can start with. If you make them too large, you can get gradients which explode. If you make them close to 0, you can have gradients which vanish, and you don't want that. So you choose typically some small values distributed according to the normal distribution. Then we need other parameters. We need to define the activation functions So W and B, they are the parameters, theta. And these are the quantities we want to optimize. The activation function must be chosen. So you can actually have different activation functions for different layers. And you will see that when we have a classification problem, if we have, let's say, 10 numbers you want to classify, you would have in the output layer, you would have a different activation function than you would have in the hidden layers. And we will see again an example of that next week when we build the code. So next week, we're just actually going to step through the elements of writing a code. And you should feel free to actually take these elements and use it in the writing of your own code for project number 2. So the activation function is something we need to specify. We can have hyperparameters and the regularization parameter, hyperparameters. So we can have this typical, the hyperparameter lambda, and we can decide whether we want to have an L2 or L1 regularization. So the typical case which you would be doing is that you would rerun the network with different activation functions and keep the same type of hyperparameters which you fixed fixed for every run. So if you want to test the sigmoid, what that gives, then you repeat, you could test the Relu function or the tan hyperbolicus and so on and so on. So the hyperparameters are parameters we need to fix. Now, this doesn't end. We need to fix the learning rate. Plus learning rate scheduler. So this could lead to things like adaptive gradient, this ADA-grad. It could lead to different schemes, like we could have a linear, we could have a constant, and we could have these second order methods which lead to ADA-grad, where we have an adaptive update of the learning rate, RMS prop, etc. Then, and as I said, this doesn't end. We need to look at the gradient approximation, whether we want to do a stochastic gradient descent or not. We need to fix the number of batches, the number of mini batches, and the number of epochs. And these are parameters, again, which we need to tune. So each of these approximations with different set of parameters. And as we saw, like the ADA-grad came with 3 more parameters which we can tune. The RMS prop comes with 4 parameters to be tuned. If we are using a stochastic gradient descent, we will have a number of epochs and number of mini batches. So we can then set up a grade. I'm just going to put this in a generic wording, like gradient descent methods. And when I say gradient descent methods, that means also stochastic gradient descent. Or it can be some kind of pseudo-Newton type of method. But you need to play around with that as well. And you see now, before we have started doing the iterations, before the first feed-forward pass, we need to set up all these kind of different ingredients. And clearly, we also need to set up an array with the inputs and an array with the outputs. So these are obvious things which we don't actually almost don't need to put up here, but we need also X and targets and T, the target. Okay, now we have defined what the network looks like. We defined the architecture, and we define the different ingredients in the different parts of the architecture. So when you have a hidden node, then you have a specific activation function which you need to define. Sometimes you can actually change activation function from layer to layer, but that's very uncommon. The most common thing is that you have the same activation functions for all the layers except for the output layer, because the output layer depends on the type of output you have. So you can have 100 hidden nodes, But if you have only 10 outputs, you need only 10 output nodes. And they can be defined by different types of activation functions. And we are coming back to that next week. I hope this doesn't look too overwhelming, or perhaps, as one student once remarked, this is very disappointing. I mean, because you have a kind of feeling that this kind of black magic algorithms don't need that much hand tuning, but they do actually. So you will often waste a lot of cycles on tuning parameters till you found perhaps the best possible representation of the mean squared error. So a very common strategy is that you tune first the hyperparameter lambda and the learning rate. So the results will typically be most sensitive to these two parameters. And then when you fix a range of lambdas and learning rates, you would then try to play around with the other parameters. So this is the standard approach in many of these neural network calculations. Then you can play around with different activation functions. You can play around with different schedulers for the learning rate and so on and so on. Okay, so now as we've gotten through the jungle of initializations, then we have initialized the W's and the B's, we've set up the X's, and then we are now ready. So while convergence criterion not met, then we start the feed forward. That's the first part. So this is the first feed forward. And let's call this step 1. Feed forward. That means that we are going to get an output at the end. So our output is then going to be equal to this A of L, and that's going to contain an input to the activation function, which then depends on the input from L minus the layer L minus 1, and this continues all the way to the first layer. And in the first layer, what we are feeding in is just the value of X times its weights. So this would be typically Z1, and that contains the values of the inputs multiplied with the weights. So let me just write that one down, of Z1, and then we have all the dots in here, and then the final parenthesis here. So this is what ensures the non-linearity, because you have a non-linear function Z, and then in every layer, you have an input from the previous layers, which are given by a non-linear function. And this is why a neural network is actually able to reproduce functions which are beyond just a linear function. And this Z1, just to put that one up, is going to be given by the weights in the first hidden layer multiplied with the input, X. That's Z1. So that's where we feed in the input. And the rest is then modulated by the different hidden layers and the activation functions till we have the final output. Then, when we have the final output, what we do now is the first back propagation stage, back prop stage. And the first back propagation stage here, we are going to repeat this till we hit the first hidden layer. So we will then repeat, we'll do this for L equal L minus 1, we do this for L minus 2, and then we move down to the first hidden layer. And then we would calculate this quantity delta J of L, which is given by the sum of K. It has the delta K from the layer ahead of it, multiplied with the weights from the layer ahead of it, L plus 1, and then this is multiplied by the derivative of the activation function of Cg of L. Then we need the gradients. So we have the gradient descent, which is applied to the weights, like we did with the parameters in linear regression and ordinary least logistic regression. So we would have a JK, which is now being updated, minus this learning rate, eta. So eta is the learning rate. And then I have a delta J of L multiplied with AK of L minus 1. So this is my gradient. And now what I have to plug in now is a learning rate. So these are the weights, and then we have the biases as well, which are updated according to the algorithm Bj of L, the previous value, minus the learning rate, multiplied with delta J of L. So now I'm putting up the learning rate without any knowledge about iterations and so on. But this is a quantity which you will then use a scheduler for. You could use AdaGrad, RMS prop, or whatever, to tune the learning rate. So these are the equations for the gradients for every single layer. Now what you see now is that if the gradient vanishes, then the training stops. Because now we are going back and forth. So when we've done this first stage, the next stage, 3, is back to 1, 1, and 2. And repeat till convergence is met. Repeat 3 till convergence is met. So this is the typical way we would go back and forth in a neural network. So we use the back propagation algorithm to find the expressions for the gradients. When we have the gradients, we can then train the weights and the biases in every single layer, but we don't want them to vanish. So when we implement logistic regression and linear regression, we want the gradients to vanish. That's the convergence criterion which we have for a linear regression and logistic regression. Here, we are looking at every node as a training element. And that means that we evaluate the gradients as a way to update the weights and the biases, the parameters of the model. But then we have a convergence criterion which measures whether the output we produce is as close as possible as it can to the targets we want to reproduce. And so that means that if we have the mean squared error, if we say that we are happy with a mean squared error of 10 to the minus 3, we stop. Or you could have a number of iterations. You could say, I'm going to do 100 iterations, and then I stop. And if it hasn't converged by then maybe I have to start thinking and do some deeper analysis. Now, so this is the basic framework which we are going to implement. Now, what we need to look at now are potential problems. And I mentioned one of the potential problems with the vanishing gradients. So let's take a look at that and how we can actually try to mend that by using different activation functions. So vanishing gradients is an inherent problem to neural networks. And if, as I said, if the gradients vanish, the training stops. So let's look at these type of problems here, because that's something which we also need to study in project number 2. So problems. And one of the problems we are going to look at is the problem of vanishing gradients. And we are going, after that, we are going to look at the functions which perhaps could actually cure that problem here. So let's now look at the case. Let's take a simple example here. And let's assume that we have just 2 layers. So we have L equal to 2 hidden layers. Actually, it's actually the hidden layer plus the output layer. Now, what we're also going to assume now is that we have a very simple case. So simple case where we only deal with scalar quantities. I mean, X has just one value, W has one value, B has one value. So we're just going to simplify things, because when we simplify here, it's going to be enough to see the potential problems. So let's assume that we have a simple case and that x, w, and b are just scalars. So what that means is that the output which I get from my hidden network, so the output, and I'm just going to call this f of x as a function of theta. So this function f is my output. This is what we called y tilde. And this is now given by the activation function in the last layer. So that depends on W2 here. And this is multiplied with the input which comes from the previous layer. So that means that this is multiplied now with sigma 1. And sigma 1 depends on W1 times x. So I'm just making a very simple model. So W is not a vector or a matrix, it's just a number, W1. And x is just a number, and then plus b. Like that. And sorry, I just forgot one thing here. And then I have a bias, so this is a B1 plus a B2. So this is just as simple as I can set up the network. 1x fed in, multiplied with a weight, feeds into the hidden layer, which then produces an output in terms of this sigma 1, and that feeds into the final layer. Does that sound okay? So what I need now is to take derivatives. So when I want the gradients, so one thing I want to, so this is my output. So I need derivatives with respect to the different omegas. So these are the parameters. So if I look at the derivative with respect to this omega 1, for instance, what I would have then is a derivative. I'm just using the standard rules for derivatives now. I would have a W2 multiplied with a sigma 1, and then I should now, I'm going to repeat this over to this line here. So this has an argument, W1 of x plus B1, end parenthesis, plus B2. And this is now multiplied. So this is just a multiplication sign. This is multiplied with the W2 times the derivative of sigma 1, W1 of x plus B1. And this is obviously, so this is a multiplication sign. I'm just circling it out, and this is actually an x. So this is my derivative. Now, if I now increase this, and I have many layers, with many layers L, what I end up with then is a derivative for this output. And this is a quantity which we need to deal with when we are taking the derivative of the cost function, because this output enters the cost function. So this is a gradient which we need to calculate. It's not the final derivative of the cost function, but it's a quantity which enters the cost function derivative. And you can quickly see how this can pose problems. So this will be the product. I would have an L equal 2 here up to L. And then I have my W2 here. And this is multiplied with, so I have now my multiplication from L equal 1 to the final layer of sigma z prime. And this takes an input, z of L. And then finally, this is actually multiplied with x, because we have the x which comes out here, as you can see. The x here is also repeated in here. So this should be actually a multiplied with this quantity here. And this z of L, if we look into it, this is the same as the quantity, the output. It's actually the output from the previous layer. So this is an output from what comes before, from the different layers from L equal L minus 1, L minus 2, etc. And this is going to have a sigma L minus 1, and this has an A L minus 1, and this has again all the way down to sigma 1 of A1 of X, and then the end of all these parentheses. So now if we look at the case of the sigmoid function, if this sigma L is a sigmoid function, so I have a L down here, is a sigmoid function, then if this argument z of L, the absolute value, is much, much larger than 0, then if we look at the sigmoid function, if we plot it, so suppose we make a plot of the sigmoid function, then the sigmoid function, if we now have 0 here, and then we have 1 here, so the sigmoid function takes a value like this. And what you see now as a function of z of L, so this will be sigma of L. If you now look at the function, when z of L is very large, then the function is almost a constant. When it's a constant, then the derivative is getting close to 0. So then, this sigma derivative of L, of z of L, goes to 0. And if you go back to the equations then, so if the derivatives are small, what we are doing then in the equations, so I can just keep this for just a moment. So when the derivatives is small, and since we now are having a repeated implementations of the derivatives in here, so you see now we have all the derivatives which come in here. So we are multiplying small numbers with small numbers. So if you happen to have large values of z of L, since the derivative of this sigma function enters the calculations of the gradients, as we saw in the equations, so the derivative of the activation function plays an important role, then we can actually get gradients which start to vanish. So if I have 10 to the minus 2 multiplied with 10 to the minus 2 in the next step, then I'm quickly piling up numbers which lead to smaller and smaller contributions. And then if the gradients vanish, then my trading stops. And this is an unwanted feature. So you can easily see from this kind of chain of calculations what the impact of a small derivative of the activation function can be. So in this simple example, just to quickly go through it again, we started first with 2 layers, and you see now that this is now given by the derivative of the function contains a derivative here, and it contains a derivative here. So what that means is we can rewrite it in terms of a product of a series of derivatives here. And clearly, if they are small, then we are running into problems. So this has led to actually people trying to find other types of activation functions which can cure this problem. So let's look at the list of potential candidates. And this list is by no means exhaustive. There are tons of activation functions. And if you can cook up an interesting activation function, you will again find many new friends who may be willing to cite you. So this is again a field which is very, very important in machine learning. So let's look at some of the potential activation functions. So this is just a preliminary list of the sigma functions, sigma z of L. Let us just call them sigma of z. So one function which you will encounter, which we already have encountered, is the rectified linear unit. And this is normally called ReLU. And the function is given by a S sigma, which is given by the max value of 0 and z. So z is the input. And you see that the derivative is given by c0. See, the derivative is equal to 1 for z larger than 0. Now, there is a rectification of the rectified one by allowing for a term which takes into account negative values of z. And that has a new name. So this is just one of the functions which is being used. And it's not called the rectified linear unit, but it's actually called the leaky ReLU. And the leaky ReLU has the following values. Sigma z is equal to, so we have the same type of function here. We have a max as before. So we have a max 0 and z when z is larger or equal than 0. And then we have a, which basically means z, right? So we don't need to put the max function, we can just put z. So I'm just going to take away the max function here, or just rewrite it. You can just write it that's equal to z if z is larger or equal than 0. And then it's equal to a constant, which is normally small, alpha. And this is a typical small parameter. So this could be typically 0.01 for z less than 0. That means that the derivative, or rather it's actually alpha times z. So that means that the derivative of this function is now given by z, this parameter alpha, when z is less than 0, and 1 when z is larger or equal than 0. So here are two other functions which many people actually play around with. We also have another function which is called the exponential linear unit, and this is normally called an ELU. This is also an option. In that case, what we would have is a sigma z, which is given by the following function. So again, I have a parameter alpha, which needs to be set up of e to the power of z minus 1 when z is less than 0, and then z when it's larger or equal to 0. And that has a derivative which is given by the parameter alpha of e times z when z is less than 0, and then it's given by 1 when z is larger than 0 or equal than 0. So that's the ELU function. The thing which is important with these types of functions is that, one, you have a simple derivative, and it's easy to calculate, and it has the kind of properties we want to have with these activation functions, in particular if we are looking at classification problems. Then, just to conclude here, we have two more. So the next one is the tan function, and then sigma z. These are the last things which we're going to put up today. This sigma z is just given by tan h of z, and then we know that the derivative of this function is just 1 minus tan h of z squared. So that's another function which is widely used. And finally, we have the sigmoid function. And for the sigmoid, we have sigma z is equal to 1 divided by 1 plus z minus z. And the derivative is the one which we have already encountered, and that's given by sigma z of 1 minus sigma z. And I'd say, almost unfortunately, There is no kind of magic activation functions, and people often end up playing around with different types of activation functions. So in project number 2, you're actually tasked with trying out some of these functions and look at the final result which you get for a classification problem and a regression problem. So this is going to end today's lecture. Next week, the one thing I wanted to say something about is the universal approximation theorem, and then we are going to move on to the setup and development of a neural network code, which is something you will find very useful for project number 2, and where the main task is actually to do both a classification problem and a function fitting problem with a neural network. So that's the basic task for the next project. And the hope then is that we can demystify many of these kind of black box feelings which we have towards deep learning and neural networks when you actually have written your own code. I think that's an important aspect of understanding the basics of central machine learning algorithms. Okay, I'm going to stop the recording now. And as usual, we are going to put everything online. So you will find the recordings